In recent years, the U.S. and Japan have engaged in intense negotiations regarding restriction on trade between the two countries. One of the claims made repeatedly by U.S. officials is that many Japanese manufacturers price their goods higher in Japan than in the U.S., in effect subsidizing low prices in the U.S. by extremely high prices in Japan. According to the U.S. argument, Japan accomplishes this by keeping competitive U.S. goods from reaching the Japanese marketplace. An economist decided to test the hypothesis that higher retail prices are being charged for Japanese cars in Japan than in the U.S. He obtained samples of 50 retail sales in the U.S. and 50 retail sales in Japan over the same time period and for the same model of automobile, and converted the Japanese sales prices from yen to dollars using current conversion rates. The following values from these two samples were obtained. I'm going to go ahead and let population 1 be the Japanese cars sold in Japan, and population 2 be the Japanese cars sold in the U.S. What I want to do is to try to estimate the difference in the average prices. Now we are told that 50 cars were sampled in Japan and 50 cars were sampled out of the cars in the U.S. And the average and standard deviation of those samples was obtained. X sub 1 bar, the sample that was taken out of population 1, gave an average of $17,236 for the price of the cars, and a sample standard deviation of $1,974.09. The sample size, N1, was given as 50. The U.S. cars were also sampled, and a sample average of those 50 was obtained. It turned out that the U.S. cars averaged, the 50 U.S. cars from the sample averaged $16,596 with a sample standard deviation of 1,981.44 cents. The sample size for this population 2 was also given as 50. Now, as mentioned earlier, we want a point estimate, an estimate of the difference in the overall population averages. And to do that, we're going to take x1 bar minus x2 bar. So that's basically the 17,236 subtract 16,596 to give us a value of $640. So I guess there is some evidence that the U.S. officials saying that the Japanese are charging more for their cars in Japan than in the United States. There might be some evidence of that. It turns out that they, based on the samples anyway, the average from the sample for Japan is higher than the average from the sample in the United States. So that's a $640 difference. But we cannot say right now that Japanese are doing this. This is just based on 50 cars taken out of each market. So we can't go ahead and conclude from that what's happening with all the cars in each market. So it's just sample evidence, if you will. If we actually knew what the difference in the population average values were, we could determine right away whether that was going on or not. But that would mean that we would have to their sample would be the entire population, and that would take into consideration all of the cars sold in each country for that particular model. So we're not going to be able to do that. But what we have is an estimate of that, and that would be the x1 bar minus x2 bar, and that estimates, it's called a point estimate of mu1 minus mu2, and that is the $640. Now we do have the sample standard deviation, so we have some estimate of the variation in the prices in each country, and from that we can build a sampling distribution. And through the sampling distribution we can attach a probability statement to this problem by building a confidence interval. We want to say with 95% confidence how close this $640 is to the real difference in population averages mu1 minus mu2. So to build that confidence interval, the first thing I need to do is determine if sigma is known or sigma is unknown. And in this case, we have sample standard deviations, and we're going to go ahead and consider sigma unknown. We have estimates of sigma 1 with S1 and sigma 2 with S2, but these are estimates, so we're going to go ahead and build a t-distribution for our confidence interval. Our formula for this confidence interval is given here in the blue box, and I already have a point estimate value for the difference in the population averages. I got a difference in the sample averages, and I've got that at 640. I now need to get a standard error value, so let's go ahead and compute that. I would have the 1974.09, and I've got to square that, put that over 50, and the 1981.44, square that, put that over 50, and take the square root of the whole thing. And when I do that with my calculator, I get 395.55. Now, the more challenging part of the confidence interval for sigma unknown is getting our our critical value, my T alpha over 2, and this is a 95% confidence interval, so I've got 0.05 over 2, which is T sub 0.025. And I'm going to use the T distribution table. So the column that I'll be looking down is 0.025. For two populations, the degrees of freedom is given by a messy formula, and you can look at that formula on your formula sheet for Chapter 10. I'm going to go ahead and put the values in the correct place here. And again, this is quite a calculation. So it'll be the 1974.09 squared divided by 50, and the 1900, this is my S2 value. I'm going to do the same thing. Now if you're going to do this calculation in your calculator, you really need to practice it a little bit, because you got to follow the order of operations and get everything in there and calculated according to the way the formula is laid out. So I'm just putting all my values into the formula. My N1 is 50, my N2 is 50, and the denominator there, I'm going to take 1 over 50 minus 1 times the 1974.09 again, the S1, squared over 50, and squaring that. And pretty much do the same thing with my the information from the second sample. So 1981.44 squared over 50, and then square that. Now I get 97.99 degrees of freedom. And to be conservative for the degrees of freedom, you actually round down. So that would technically be a 97. As far as testing purposes or anything, if you said 98 there, I wouldn't be taking anything off. But according to the rules, it should be rounded down for degrees of freedom. Now, what I'm going to do is I have enough information to go to the table. My .025 along with row 97 in the t-distribution table gives me a t-value of 1.985. So this degrees of freedom here, again, is a complicated, tedious, I should say, calculation. So to do that by hand using the formula, I've got to run through several calculations, and I have to make sure that I'm following the direction given by the formula as far as what order to do those calculations in. But anyway, I think I have all the pieces I need now to build this confidence interval. I have the point estimate, the x1 bar minus x2 bar. I have the t alpha over 2 value, and I have the standard error value. So putting all of those into the formula, I get 640 plus or minus 1.985 times the 395.55, and doing the margin of error, I'm multiplying the t alpha value with the standard error, so I get 785.17, and a confidence interval of negative 145.2 to 1,425.2. My margin of error is $785.17. So that is my margin of error. Now remember that the $640 is an estimate of the difference in average prices between the two countries. The $640 is an estimate of the difference in the average prices, right? The question that a confidence interval answers is, how far off could that estimate be from the real difference in average prices? Well, it could be as much as $785.17 off. In other words, mu1 minus mu2, the difference in population average prices, I'm 95% sure that that difference is somewhere between a negative $145.20 and $1,425.20. So I'm 95% confident that the real difference in average prices is somewhere between those two values. So I put a little number line down there to try to give a graphic of this confidence interval. The negative 145.20 is to the left of 0, and the 1425.20 is to the right, although much further to the right. The $640, which is my best guess, that's my point estimate, is right in the middle. So with a 95% confidence interval, there is some allowance that the difference could either be positive or negative, indicating that either the average prices for the cars in Japan is greater than the average prices in the U.S., and also the possibility that the average prices in the U.S. are greater than the average prices in Japan. Now, it seems like there's more probability that the average prices in Japan is higher. We don't have the 95% confidence that that is true. And I'd venture to guess that if we ran a hypothesis test on this, with alpha equal to 0.05, we would not be able to conclude that Japan is indeed charging higher prices on average for their cars in Japan as opposed to the United States. Now, the last thing I want to do before we go ahead and run a hypothesis test on this is to draw my conclusion, and it would be stated this way. I am 95% confident that the real population difference in the average prices is somewhere between negative $145.20 and $1,425.20.